Uh, Good evening, everybody. Hopefully you can hear me. Can I just ask Dan to give us a signal to make sure he's all prepped at his end?
I'm here and good to go, Brian.
Brilliant, brilliant. Thanks, Dan. So, just by means of an introduction, my name is Brian Lawson. I'm the Technical Director for Projex Solutions, who are a project management and engineering services organisation. We're based in our head offices in Brighouse in West Yorkshire. We also have a satellite office in Teesside. We're hosting these lectures in support of the West Yorkshire Area IMechE committee. This lecture is the title is Basic Steam System Design Considerations, and it's the second of a series of 8. The lectures this time have been run in collaboration with the University of Huddersfield. So it's a big thank you to Josh and Carl in the engineering department who've collaborated with us to hold the first face-to-face last week in the university, and now we've got 7 on the bounce on Teams. The lectures are read and presented by Dan Wells, who's the National Consultant Specialist for Spirax Sarco, and you'll hear Dan's voice shortly when I hand over to him. Just some basic logistics. The presentation will last for around about 45-50 minutes. And there'll be an opportunity for Q&As at the end. The simplest way to do that is to use the chat function of Teams to ask any questions for clarification. So without further ado, I'll hand over to you, Dan.
Great. Thank you very much for that introduction, Brian. Much appreciated. And just to echo the thanks to the team at Projex, the team at the Institute of Mechanical Engineers for West Yorkshire, and also the team at Huddersfield University, without which this series of presentations wouldn't really be possible. So it was a great attendance we had at the presentation last week, and many thanks for those of you that came along. And at that time, I gave a very broad high level to Spirax Sarco as an organisation to give you an understanding that we are a global entity, but we are still very much a British company, a British-owned company that does the vast majority of our manufacturing here in the UK. So please don't let anybody tell you that the UK doesn't manufacture anything anymore, because that's simply not the case. So under the Spirax Sarco group of companies, we've got our steam thermal solutions stream, we've got our electrical stream, and we've got our fluid technology stream. But we're also investing heavily in new innovations such as steam heat pumps, and also steam that can be produced by means of thermal storage. For example, with molten salt releasing its energy to generate steam. So moving forwards, I've introduced Spirax Sarco's range of resources that you can very, very easily access on our website, together with those calculators and configurators, which, as you'll remember, are useful for not just helping us with the basis of design for a steam system, for example, by understanding the amount of heat energy that's required by a process, we can calculate the mass of steam that's required and therefore the resulting control valves and steam traps and heat exchangers. But we can also use those calculators to help our client understand their cost of steam. That's critically important. How much does it cost to produce a ton of steam? And that's something that we need to be mindful of. Because if we can start a project with a clear understanding of the cost of steam, when we've engineered certain improvements with how we generate the steam, distribute the steam, or use the steam at the process, then by reducing the mass of steam that's required, the boiler doesn't have to work as hard, it doesn't have to consume as much gas, and we don't have as many carbon emissions. So by understanding the cost of steam, we can demonstrate what the financial payback is for those improvements that we've introduced. So please do check out those resources, those calculators and those configurators on our website. As Brian mentioned, this is a series of presentations, and last week we looked at the fundamentals of steam, the basic principles of steam. We looked at the steam tables in some detail. The overall message of that particular presentation was it's critically important to keep the condition of the steam as dry as we possibly can at the point of generation. So today we're going to move forwards and we're going to look at the topic of the considerations that we need to take on board to apply best practice in how we move the steam from the point of generation, what could be thousands and thousands of meters around site, so it can arrive at the point of use at the best condition. So just to give a very, very quick recap of some of the learning points that we went through last week, the properties of steam and the advantages that that brings are completely different to a hot water-based system, for example. Notably, it's a compressible gas, which means at a high pressure, we've compressed that volume, so we can now move it in a very, very small and cost-effective infrastructure without the need for those circulating pumps as we would do with a water-based system. We've got that pressure-temperature relationship. If we know the pressure of the steam, we know its temperature. That doesn't apply to a water-based system. It's very, very densely packed with energy, and it gives up its heat energy by condensing rather than by cooling down, which means that not only do we need a very, very small steam boiler and distribution network, but we also need a much, much smaller heat exchanger when compared to a liquid-based hot water system, for example. So the slide that I promised you I would show again. Here we go. The single most important slide that I ever show in any of my presentations. So if we start off by looking at the steam tables over towards the left-hand side of the screen, they bring together a lot of those different relationships that we spoke about. The first two columns, we've got that pressure-temperature relationship. By understanding the pressure of the steam, we know its temperature, and vice versa. If we need to achieve a particular temperature, we can achieve that by nothing more than manipulating the pressure. It's why those very, very simple two-port spring-acting pressure-reducing valves are so useful to us in controlling the steam. But it also tells us why we need a good number of pressure gauges around the infrastructure. Without those pressure gauges, we don't have any understanding of what's actually happening in the steam system. And then we've got the pressure-volume relationship. We know the pressure of the steam, we know the volume that steam occupies. In the middle, you can see the three columns that represent the energy content of the steam. So first of all, the column headed water. That's the energy that the water needs to contain before it reaches the boil. Now, obviously, if we're putting hot water into the boiler, as a result of returning more condensate, we don't need to consume as much gas, the cost of steam will be reduced, and those carbon emissions will be reduced as well. So that really reminds us of the fundamental importance of recovering as much of that hot condensate as we possibly can. But even then, we're only going to have hot water. The next column, that demonstrates the additional energy that we need to add to that boiling water to bring it to the boil. So if we add the two columns together, that gives us the total heat energy that steam carries. Now, when the steam's carried that heat energy thousands of meters around site, the steam hits the heat exchanger, the process, and condenses. Remember, the only way that steam can give up its energy is by condensing, by changing state from a gas to a liquid. And when that happens, it's the energy demonstrated in this column. That's the energy that moves across the thermal barrier to heat the process. So if I had my way, I'd draw a line through the enthalpy of evaporation, and I'd simply call it the useful heat energy. So when we take the useful heat energy away from the total heat energy, the energy that remains in that liquid condensate is exactly the same as the energy that appears in this column. So it really demonstrates the value of getting as much of that condensate back to the boiler house as we possibly can. That hot water is going to give us a really, really good head start in producing steam efficiently. Now, all of these values change as we increase the pressure of the boiler. So, for example, at 10 bar gauge, water boils at 184 degrees. You can see that we've got to have more energy in the water before it hits the boil. So that tells us that it becomes all the more important for us to recover that condensate. It tells us there's more total heat energy present within the steam, and it tells us that steam will have a smaller volume. But remember, it's the middle column. That's the useful heat energy. And you'll notice there's actually more total heat in steam, and it exists at a higher temperature, at a higher pressure, but there's more energy in the steam at a lower pressure. So for that reason, I encourage you, please don't confuse the issue of temperature with the issue of energy. They're two completely different concepts. And of course, moving across to the opposite side of the screen, the temperature enthalpy curve really plots the journey that water takes as it boils off and changes state to steam in the boiler. But it will only do so when it's got the appropriate energy content. So the overall aim of steam generation is to ensure that the steam exists on the dry saturated steam line, or as close to the dry saturated steam line as is possible. If we don't have dry saturated steam, if the steam sits in the wet steam zone here, then we're likely to encounter those issues that we discussed in some detail last week. We're likely to encounter more erosion, more corrosion, and more water hammer in the infrastructure. But we're also going to get those inefficiencies, because it means that if we've got very, very wet steam, it's far more likely to give up its heat energy and condense in that distribution pipework. For example, we could be putting 10,000 kilograms of steam into the pipe, but we may only be getting 9,000 kilograms out of the other end, because it means that a ton of steam, beg your pardon, will be condensing in the pipework as it's giving up its heat energy to that carbon steel infrastructure. So simply put, the drier the steam going into the pipework, the less likely it is to condense, and the greater the efficiency we're going to enjoy, because we're getting more of the steam out at the other end. The two benefits, well, it means the heat exchanger is likely to be sized correctly, and it also means that the boiler doesn't have to work harder to replace the steam that is condensing in the pipework. So the idea really is for us to get the steam to the point of use as close to that red dry saturated steam line as we possibly can. So last week we spoke about those two fundamental relationships in some detail, the pressure volume and the pressure temperature relationship. And we also understand that one of the fundamental causes of an inefficiency in a steam system is when a steam trap fails in the open position. Because we need the pressure drop across the steam trap, we need a positive pressure on the steam side that's pushing the condensate away to the lower side downstream of the trap. It tells us that if that trap were to fail in the open position, the effect of that steam as it depressurizes and expands significantly means that we've got to vent it away from the condensate infrastructure, because if we don't, we're going to experience a significant amount of damage. And similarly, any high temperature, high pressure, high energy condensate that exists upstream of the steam trap, that too could depressurize from a very high temperature to a much lower pressure where it can only exist at a lower temperature. So as that condensate depressurizes, a certain mass, a certain volume's got to boil off, change state from a liquid back to steam as a gas again, and it's going to expand to a significant factor, maybe as high as 1,600 times greater in volume than when that condensate exists as a single phase liquid. And the pipework downstream of the steam trap, that's been sized to accommodate condensate as a liquid. So it can't contain that expansion. We've got to vent it away to protect the infrastructure from any damage. Fortunately, as we vent that expansion away, in many cases, we're simply heating the car park up. It means the boiler's got to work harder and harder to replace that missing steam. Our cost of gas, our cost of steam, and our carbon emissions are going to increase significantly. So those vents really are the first visual check that we want to keep an eye out for to understand the overall health of the wider steam trap population. So last week we looked at the boiler house in some considerable detail to understand the best practice we need to employ at the point of generation to control the steam boiler correctly and to ensure that not only are we producing steam rapidly whenever there's a demand, not only are we producing the steam efficiently by not consuming too much gas or producing too many carbon emissions, but also to ensure that we're producing the best possible quality and condition of steam. Remember, we want the steam to be as dry as possible going into the pipework to reduce the burden of maintenance and to ensure that we're not having too much of a heat loss in the infrastructure, but also to ensure that the steam is very dense with energy so we can ensure that the process is taking place as efficiently as we can, what could be thousands of meters away. So we remember all of those controls and ancillaries that we discussed, the level controls, the blowdown controls, and most importantly of all, keeping the water in storage at a nice high temperature so that we can achieve all of those things. But even when we are following best practice at the point of generation, we've still then got to move the steam, what could be thousands of meters around site, so it can move from the energy center to the various plant rooms and arrive at the heat exchanger at its best condition, as dry as we can, with as much energy as we can possibly expect. The problem is that distribution pipework, it's one big radiator. So if we're distributing steam at 10 bar gauge, 184 degrees, if we've got a carbon steel infrastructure, if it's oversized, if we've got very wet steam, if we've got missing or damaged insulation, if that pipework's running outside and it's a very cold day, we're going to get a significant amount of heat loss. So it's important that we apply the best possible practice we can in order to keep that heat loss at its absolute minimum and to get the steam to the point of use as efficiently as we possibly can. So that's what we're really going to look at in some detail today. So when we're talking about a good condition of steam, we're talking about plant steam here. We're not talking about steam for critical applications like food and beverage or pharmaceutical applications where the steam could come into contact with that product and therefore would need to be considered an ingredient. So when we're talking about plant steam as a utility, we're typically talking about keeping it in a good condition, which means keeping it as dry as we can. We do that by getting rid of as much of the condensate as we possibly can across those steam traps. Keeping it free of any rust or scale or particulate that could result in erosion or blocked orifices of steam traps and control valves. We need to vent away air and any other non-condensable gases. Some of those items of capital equipment, they will require periodic maintenance. So it's vitally important that we make provision for being able to isolate them safely. And then we also need to ensure that the pipework itself has been correctly sized. Remember, with the steam system, we don't pump steam. Unlike a water-based system, it can only move in accordance with the pressure drop around the infrastructure. So it's vitally important that we size those pipes correctly. So one of the benefits of a nice high pressure steam system is by compressing the steam so it occupies a small volume, then the pipe diameter is small. So obviously that keeps the overall infrastructure at a nice, attractive capital cost. A lower pressure steam is going to have a higher pipe, a larger volume, and therefore will require a bigger pipe diameter. So the cost can be significantly greater there. But another benefit is by keeping the pipe diameter nice and small, we've reduced the mass of that radiator. So it's less likely that that steam is going to condense out in the pipework. So if we're putting 10,000 kilograms of steam out of the boiler into the pipework, we're far more likely to be getting closer to 10,000 kilograms of steam out the other end. The boiler doesn't have to work as hard. We're not consuming as much gas. The cost of steam and those carbon emissions are going to fall. Other benefits are if we've got drier steam and we don't have as much condensate sloshing about in the pipes, we're not going to need as many steam traps. So we're reducing the capital cost further still. And we've reduced the risk that those steam traps could fail in the open position. So we're helping to safeguard against those losses and inefficiencies. And if we've got drier steam as a result of there not being as much condensate in the pipe, we've minimised the risk of any erosion, corrosion, water hammer. So we've reduced our burden of maintenance. And it also means if the steam's drier, there's more energy in it. So the boiler doesn't have to work as hard. And we're bringing the condition of the steam closer and closer to that red, dry, saturated steam line, meaning the heat exchangers and the process time, it's all going to work more efficiently. So pipe sizing is critically important. I don't want this slide to scare you. It really just reminds us that there is a methodology we need to employ when we're sizing the steam pipeworks. When we're sizing in accordance with the pressure drop method at the top of the screen, it means we need to take into account the mass of steam that we're moving. We need to take into account the boiler pressure and then the pressure at the heat exchanger, the reduced pressure. But we also need to take into account the resistance in the pipework in the middle. That's what's going to result in the movement of the steam around the infrastructure. The velocity method that you can see in the bottom left right-hand corner, that's really the speed that the steam's moving at. Now, if we'd made the mistake of thinking that steam was a gas, or if it was in the perfectly dry condition, as it is referenced by the steam tables, then we may look at moving the steam at perhaps 40 meters per second. Now, that's about 90 miles an hour. So if there was any rust or scale that was present within the steam, as a result of that erosion or moisture being present, if we're moving that at 90 miles an hour, that's very, very quickly going to create more and more problems of erosion of sensitive items of capital equipment like control valves or pressure reducing valves or even flow meters. So if we suspected that the steam was known to be in a poor condition, we'd want to move the steam at a much more gradual velocity, 15 meters per second, for example. The reality is the vast majority of design engineers are simply not going to know what that condition is going to exist at because it varies, it changes throughout the day. So the safe spot is probably sizing at around 25 meters per second velocity. That way we can have peace of mind that we shouldn't have too many problems with an excess of erosion as a result of that poor quality steam. So we need to get that condensate out of the infrastructure very, very quickly. We're going to have a biphase in the pipework. We're going to have the steam as a gas with all of that useful energy in it that wants to move at a very fast velocity. And we're going to have the condensate as a liquid as a result of that heat loss that we need to drain away. So we need to separate the two. So we need to apply best practice to get that condensate away as quickly as we can so we don't have problems with that erosion, corrosion, and especially that water hammer. So the image I'm showing at the moment, it's an image of what we call, this is actually steam hammer. So this is a condensate flooded pipe. And you can see that the steam that is introduced into the pipe wants to move at a much, much faster velocity than the condensate does. And then as the steam moves from the from one side of the screen to the other, that steam then condenses as it gives up its energy. So as that steam condenses and collapses, it pulls a vacuum. So the same thing happens all over again. So it reminds us how vitally important it is to get that condensate away and separate the steam and the condensate. Other good practice, we want to ensure that we've got a rise and fall in the distribution pipework, as you can see at the top of the page. The fall in the pipework needs to be in the direction of steam flow. And that means that we've got the movement of the steam and gravity helping the condensate move to a well-designed and a well-engineered steam trapping station. That's when the condensate can drain away and the steam can remain in the infrastructure. Another best practice, like taking the steam away from the top of the distribution pipework, not the bottom and not the side, because that way we run the risk of flooding that heat exchanger with an excess of that liquid condensate that simply doesn't have enough heat energy present within it. So the video I'm showing at the moment is it's a gasket that's blowing. We've got a pressurized steam pipe that's pushing that condensate along, and it's resulting in some of that water hammer that we've spoken about. And the water hammer has actually caused the gasket to rupture on this occasion. So what's likely to happen here is in 5, 6, 7, 8 weeks time, the engineering team will have the opportunity to close off the steam system, let it cool down and depressurize. They'll pull apart those flanges and they'll probably replace the gasket. The problem is, as soon as the steam system is re-energized, the exact same thing will happen. Because if we're moving steam at 40 meters per second, that buildup of pressure that's causing that water hammer is forcing the condensate across the flanges and the gaskets at such a pressure that it's causing the flanges themselves to erode, which is resulting in that passing condensate, that water hammer effect. So it'd be advised to take a broader look at the overall infrastructure and find the root cause of the problem. And it could be down to a number of things. It could be down to the fact that the boiler is producing steam that is very, very wet, and therefore it's condensing out in the pipework. Therefore, we've got a very large condensate load. The steam traps could be undersized. The steam traps could be failed in the closed position. We could have damaged insulation, which means we've got more heat loss than we're expecting. We could have undersized pipework, which means the condensate and the steam are moving at too great a velocity. The reality is it could be any combination. It could be any or even all of those things put together. But it means that in a situation such as this, we'd want to stop and really look at the steam distribution system holistically to identify what the root cause problem really is. So getting that condensate away is critically important. We want to ensure that we've got a well-designed, well-engineered steam trapping station. Typically, it's a downward pointing T. That T should be line size, and we should have a dropper leg on the T that's got a vertical drop of probably 2 pipe diameters. That way, it's a very, very generous reservoir. So any condensate that's present in the infrastructure can drain out quickly and easily. We can get that condensate away, but we can ensure that the steam remains at its driest. Other things that we want to give thought to are we want to get the air away from the steam system. Now, we always treat the water in the boiler, but that's primarily to protect the boiler itself from the result of oxygen corrosion or oxygen pitting. We can never guarantee that we're getting oxygen and other non-condensable gases out of the steam system. And that's because when a steam system's switched off, the steam condenses, and therefore it pulls a vacuum. So it could be pulling air in from valve spindles, gaskets, vacuum breakers, for example. It's important that we get that air away, because if that air is left in the infrastructure, that can be the #1 cause of corrosion that we experience. So if you think about whenever steam's carrying air with it, when it condenses, the air becomes absorbed back into the condensate. That condensate becomes carbonic acid. That's what creates the corrosion. Boilers they actually like alkaline water. So if we get acidic condensate back to the boiler house, we've got to consume more chemicals, and therefore our cost of steam increases. And the other problem with having too much air in a steam system is Well, it's like failing to bleed your radiators at home. That air is a massive, massive barrier to heat exchange. It's going to cause the process time to slow down, and therefore the heat exchanger is going to call for more and more steam. Boiler's got to work harder, cost of steam, the cost of gas, and those carbon emissions are all going to increase. So the best way for us to get the air out of the infrastructure is using a thermostatic air vent, never a mechanical air vent that we commonly use on a water-based system, because they work on the density principle. Air and water have got different densities. The problem is air and steam have got very, very similar densities. But because they've got different temperatures, that thermostatic principle works perfectly. Whenever we've got a lot of air in the steam system, for example, when we're starting it up from cold, the steam pressure, it will move around the infrastructure like a piston, pushing the air ahead of it. So the air will escape across the vent. Then when the capsule sees a higher temperature present within the steam, it will cause that expansion to push down a ball bearing and close the vent. So we look at an air vent at every heat exchanger on the opposite side of the steam inlet. By doing so, it means we can warm the heat exchanger up very, very quickly. The very, very end of every distribution network, the air is going to rise to the high point, the condensate is going to fall to the low point, and then at the occasional high point, for example, if that pipework needs to rise to climb over an infrastructure, that's where we want to position that air vent to make sure that we don't have a bubble of air that's trapped that could result in an inefficiency. So isolation is also critically important with steam systems. We never really want to see a quarter turn valve used on a steam system for two reasons. For example, a ball valve or a butterfly valve, they operate very, very quickly. And the problem that can cause is if we've got any trapped condensate, it's really going to result in a likelihood of water hammer taking place. Opening that valve very quickly, we're going to get a huge pressure drop and we're going to get that knocking, banging, that violent vibration as a result of that water hammer. The other reason is a ball valve and a butterfly valve, they've got very, very smooth sealing surfaces. So they're more susceptible to erosion, especially if we've got a poor condition of steam. So it's very, very difficult to guarantee safe isolation. So we prefer to see a piston valve or a globe valve because they're very, very slow operating. So we're not likely to get that water hammer effect, but they're more forgiving against erosion. The thing to bear in mind here is a valve on a steam system should never be cast iron. We never want to see any cast iron component on a steam system. Cast iron, simply put, is far, far too brittle to stand up to the risk of any water hammer taking place. So as an absolute minimum, the ancillaries, the components should be what we call SG iron. That's spheroidal graphite iron. It stands up to water hammer a little bit better than cast iron. Better still, if we can move towards cast steel, that really is best practice. So the valve you can see on the screen, it's actually what we call a bellows sealed valve. Bellows sealed means we've eliminated the risk of any steam passing up the spindle, which could result in a nasty health and safety incident if and when those seals were to dry out and rupture. But even when we've got a box fresh valve, even when it's fresh off the production line, it is only ever going to be capable of isolating with a 99.99 efficiency. So that means that it doesn't really matter what the condition of steam is. There is always going to be a risk that there's a very, very small amount of steam that is leaking across those valve seats because the metal to metal, the highly polished surfaces. If we've installed that valve on a very, very poor condition or poor quality of steam, we can't really explain what the effects of erosion is likely to be. So in other words, all bets are off. Now, quite a lot of our clients, especially those that are distributing large masses of steam at high pressures and temperatures, they will refer to what we call double block and bleed or safe isolation standards. As you can see up in the little pop out at the top corner of the screen, this is actually 3 individual valves. So if there were a risk of that first metal to metal valve eroding, any steam that is passing across, that could obviously create a health and safety incident to anyone that may be thinking they're working on a process safely. So we install a second valve downstream, the idea being that we've got a second chance of that leaking steam from being isolated and resulting in a health and safety incident. The question is, how do we know that that primary valve has failed, and how do we know that the secondary valve isn't going to do the same? Well, we pull those 2 valves apart and we've got a third valve in the middle. It's what we call a bleed valve or a telltale. So when these 2 valves are locked off, this valve's in the fully open position. Any steam that's passing across this first valve is going to follow that pressure drop principle we spoke about. It's going to be diverted away. And if this telltale is bleeding away to a ton dish in the corner of the plant room, flash steam emissions that are wisping away from the corner of the plant room, they give us a visual indication. They give us a telltale to advise that that primary valve is passing, but most importantly, it gives us peace of mind that we're working on that heat exchanger on that process safely. The thing to bear in mind is safe isolation or double block and bleed on steam systems is not mandatory. It is just guidance. Some clients will insist upon it and others won't be bothered. What we could do is, for those clients that do want to increase their health and safety approach to steam systems, they could actually use the valve that is shown in the middle of the screen. That brings together each of these 3 individual valves into the same footprint, into the same face-to-face dimension. So a client can increase their health and safety very, very quickly without the minimum of downtime or without the minimum of capital works. So insulation, I think it stands to reason that if we're distributing very, very high temperature, high pressure steam in a carbon steel infrastructure for thousands of meters, it is inevitable. We are going to experience some heat loss. But by improving the grade of insulation that we have, we can understand the improvements we've made by reducing that heat loss. If we've reduced the heat loss, less of the steam is going to condense. We're getting more steam out the other end of the pipework. The boiler doesn't have to work as hard. But it also means we don't need as many steam traps, so we've reduced the risk of failure. And it also means that by having drier steam with more energy in it, the process is going to take place more efficiently, more rapidly. And we've reduced the risk of that erosion, corrosion, and water hammer from taking place. If we know the grade of the insulation and all of the other variables, then we can demonstrate the financial cost saving, the carbon saving, and we can also demonstrate the energy that we've saved. So that can be a very attractive project for our clients. When the steam system was engineered 30, 40 years ago, steam, gas was very cheap. No one really understood or cared about carbon emissions. So back then, it may not have had a suitable grade of insulation, but today we can optimize to ensure that we're helping our clients with those targets. Other things to think about: a steam infrastructure, high temperature, high pressure, then we are going to have some expansion. We need to calculate what that expansion is likely to be and mitigate against that expansion and understand how and where to anchor different items of capital equipment. Same with pipe supports. If we've got too few pipe supports, the risk is that pipework could sag under its own weight, and it's then that it's trapping that condensate. So we need to follow that best practice, not only to generate the best quality of steam in the boiler house, but to make sure that we're moving the steam with the best design considerations in that infrastructure in the middle. And that's so we can get the best quality of steam into the plant room. And we can be using the steam in different ways. There are 2 different ways. It's what we call direct usage. That's generally when the steam is it's going to come into contact with the product or the atmosphere. So it could be humidification in a hospital operating theatre or in a pharmaceutical clean room. It could be for sterilizing a jam jar, or it could be for injecting steam directly into a vat of orange juice or milk. That's what we call a direct process. More likely, we're going to be using the steam indirectly, which means it passes across one side of a heat exchanger, it heats a process up, and we remove the condensate that is formed as a byproduct to that heat exchange. So this just really reminds us that in future presentations, we're going to look at it a little bit more detail whenever steam is used directly. It means that we've got a more critical set of criteria to give thought to, because that steam is ultimately an ingredient. We'll cover that off in a little bit more detail in a few weeks' time. So something else that we need to give thought to is getting the moisture away from the steam. By removing the moisture, we're going to have drier steam with more energy in it. We're going to have drier steam carrying less moisture, so we've minimized the risk of erosion. So we use a steam separator at this point. The steam separator, it allows that moisture to break away from the steam that is carried by. The condensed moisture is then taken away across a steam trap, and the dry steam then continues towards the process. So we've protected that capital equipment from the risk of erosion, and we've now got a nice high energy content that means the process is going to take place more rapidly or efficiently. So this is an example of a steam separator in action. You'll see the steam coming in over at the right-hand side of the screen. You'll see the moisture that the steam is carrying in the bottom of the sight glass. And by referring to the steam that is exiting the separator, you can appreciate the extent at which we've now dried that steam. You can appreciate the massive condensate that is being taken away from the steam trap at the bottom of the separator. Now, quite often, along with pressure gauges, steam separators are quite often value engineered. They may be designed in at the design stage, but they're highly likely to be removed by the installing contractor or the client at the project installation stage. When that happens, the steam is going to be wetter. So that's when those mechanical issues and those inefficiencies start to creep back in. The good news is they can be retro-engineered back in very, very quickly. So we know the importance of generating steam and distributing steam at a high pressure. High pressure, high temperature, high pressure, high volume, so smaller pipes, high pressure, smaller boiler, and high pressure, a lot of motive energy to move the steam. But we actually want to use the steam at the heat exchanger at the lowest possible pressure. More energy in the steam at a lower pressure. We can control the temperature at a lower pressure. But it also means that we can move the steam from a higher pressure to a lower pressure very, very quickly. So reducing the steam pressure is done across what we call a pressure reducing station. So if we've got the steam coming in at the far left-hand side of the screen, the first thing we do is we remove any entrained moisture across that separator. That moisture condenses and we take it away across the steam trap. We've then got what we call an isolation valve, either end of the pressure reducing station. So we can isolate for basic maintenance, but we need to isolate it in order to commission it as well. Pipe strainer with its basket on the horizontal, so we're not trapping any condensate, but we're removing that particulate. We've got a pressure gauge either side of the pressure reducing station, so we can identify when it goes into fault, and we can use it for commissioning purposes. We've got an eccentric reducer coming in and out of the pressure reducing valve, so we're not trapping any condensate. We've got another steam trapping station ahead of that final isolation valve, so we can ensure that by removing the condensate, we're not resulting in a water hammer issue if and when we're going to open that valve. And then finally, we've got a safety valve. Now, not every process will require a safety valve. If the heat exchanger is rated greater than the boiler pressure, a safety valve isn't going to be required. But when a safety valve is required, we need to have it correctly sized. It needs to be installed in the vertical without any isolation upstream or downstream. We need to have the appropriate drain points to ensure any steam that is weeping off the seats and condensing can be drained away. And we want to keep that run of pipework venting the steam away to the absolute minimum so there isn't an unnecessary back pressure there. For control valves are typically used for temperature sensitive processes. They can be electrically or pneumatically actuated. Common problems that we come across with control valves are they're very, very often oversized. If we've got an oversized control valve, the seat and the plug are likely to operate very, very close together. And that means if we're distributing steam, for example, at 40 meters per second, 90 miles an hour, that's the speed of the steam in the pipe. If that steam's being throttled as it moves across the control valve as a result of the seats operating very close together, that steam velocity could increase tenfold. Speed of sound, 350 miles an hour, 440 miles an hour. So any moisture, any rust, any scale, it's going to rip the guts out of that control valve and cause it to erode and fail very, very quickly. That means we've either got a high energy inefficiency due to the steam weeping away, or we've got a very poor control of temperature of the process. So as a rule of thumb, a control valve, when it's correctly sized, should be approximately 2 pipe diameters smaller than the upstream connecting steam pipe. Also, we want to ensure that we've got those ancillaries. We need to make sure that we're removing the moisture to keep the steam as dry as we possibly can. And it stands to reason that if we're using a control valve on steam, it needs to be a control valve that is specifically for steam. A lot of water-based control valves are what we call fast opening valves. And if we've got a fast opening valve, because it's going to operate very, very close to its seat for the vast majority of its operational life, it means that it would be far, far more susceptible to erosion and failure than a specifically designed steam control valve with an equal percentage characteristic. So last week we spoke about steam metering being critically important so we can understand the efficiency of the boiler and the cost of steam. But we want to meter the steam when we get it to each individual building or process, because we can, if we know how much steam is going into the pipe and how much is coming out of the pipe, then we know how much is condensing in the middle. In other words, we can use this to tell us how wet or how dry the steam is. We can use it to tell us if we're losing steam as a result of those failed steam traps. But we can also use it for diagnostic purposes. For example, if our steam heat exchanger is calling for more and more steam over a period of weeks, that could be that there isn't enough energy in the steam, therefore we need to supply more of the steam. In other words, the steam could simply be wetter. It could mean that the steam is carrying a lot of foam or scale that's creating a barrier to heat exchange. Again, that could tell us that there's something not quite on point with our steam generation. But steam meters, they need to be considered as a number of components rather than one standalone item. Because if we're not removing the moisture with a separator, if we're not removing the particulate with a strainer, then we're likely to get a significant amount of erosion and damage to that meter. It won't be operating efficiently. If we're not removing the condensate across a steam trap and we're not removing the air across a vent, then we could be metering something that it could be potentially 50% steam, because the other 50% could be water or it could be air. And other things that we need to do to protect the steam meter is a check valve to protect backflow. We need to have the correct linear run of pipework upstream and downstream of the meter so that we're not in a position where we've got turbulent flow or an inaccuracy with the reading. So we need to think about a meter as a station rather than a standalone device. So it's only when we've ensured that we've followed that best practice with generating the steam and distributing the steam that we can say that the steam is going to arrive at the heat exchanger at the condition that we expect. Remember, we want that steam to exist as close to or on that dry saturated steam line. So that brings us to an end for today's presentation. So hopefully you can appreciate the differences that we need to give thought to in how we move the steam across that distribution pipework. And next week, we're going to move forward and we're going to look at some considerable detail about that standalone topic of what I believe is the most important component of a steam system. That's the steam trap itself. We're going to look at how we need to remove the steam, remove the condensate, not just from the distribution pipework as a result of that heat loss, but also from the heat exchanger itself. So I'd like to leave you with this final slide. Now is the time to take a snapshot of that QR code. When we spoke last week, I introduced the concept of our Year in Industry program, but also for our graduate placements. So for those of you that may have an interest in finding out a little bit more, that QR code will take you straight to that particular page of our website where you can find a little bit more detail there. So on that note, I'd like to thank you very much for your time. I look forward to speaking to you again next week, and I'll pass back to Brian to see if there have been any questions that have been put into the chat function. Thank you.
Okay, thank you, Dan. As usual, top notch. We'll just give it a minute to see if there's any questions come in. I did like the bit about root cause analysis and understanding that we have design failures and looking at systems holistically. Really good engineering practice. And also, it never crossed my mind that steam systems can pull in air by creating vacuums, causing problems. And I think the piece on isolation, really, really important for any practitioners that are dealing with any gas or liquid under pressure, that isolation is really, really important. And the point about the block and bleed valves really does keep people safe. So if you'd like to put any questions into the chat, we can test Dan's technical knowledge.
That won't take long, Brian. But just to pull you up on the point of isolation, HSG 253. That really is the guidance document that really points us in the direction of best practice with safely isolating steam systems. The key word there is its guidance. And I'm so often called to sites where I'm really piggy in the middle between a consultant design engineer and an installing contractor, and a system may not have met the client's expectations. But it's down to communication, because if the client hasn't specified what their expectations are, then neither the installing contractor or the design engineer have done anything wrong. It's just best practice. And as we know, certain things can happen along the way where certain components are value engineered. So safe isolation, that is something that can often be overlooked, as can those pressure gauges and those separators. But they can have a huge impact on the safe and efficient operation of that steam system if they're not correctly observed.
Okay, thanks, Dan. Doesn't look as if we've got any questions this evening. So thank you to your good self. Thanks also to the Western Area IMechE Committee for supporting the lectures. The University of Huddersfield for helping to broadcast the message and get some of their students involved. And just a reminder that the next lecture will be steam trapping. It'll be on the 1st of October. So thanks very much for listening, and good night from Projex Solutions, and hopefully see you next week.
Great.
Cheers,
Thank
guys.
you. Thanks. Good evening. Thank you.
Bye.